gave you a pretty long video about rotational kinematics, and I kind of worked an example into it, but now I would like to do another example. This is rotational kinematics. So first, a problem. So a wheel starts from rest. It's going to accelerate at a rate of 7 radians per second squared to a final speed of 63 radians per second. I want to know how long this is going to take and how far the wheel rotates in this time. So I'm going to pick an axis and I'm going to go based off of that. So this can be my theta equals 0 location. This wheel is going to start rotating around this axis. And we've got a rotational rate, so I'm going to just jump right into setting up a table. Back when I did linear kinematics, I would have set up this table. But these aren't the quantities I'm working with anymore, so I want to change these. I'm going to set up instead a table of the rotational quantities. X becomes theta, V becomes omega, A becomes alpha, T stays put. These are exactly the same variables that I had, they just have the word angular in front of them now. Angular position, angular velocity, angular acceleration. So I'm going to fill in what I can. I'm starting from rest, so I have an initial speed of 0, or an initial angular speed of 0. I'm going to a top speed of 63 radians per second. That sounds like a final speed. I can start anywhere I want. 0 is a great place to start. And I have an acceleration. I don't know the final position, but that's question number 2. I don't know the time, but that's question number 1, so I'm going to solve for that first. I will move this thing over and write out my kinematic equations. I'll write out the linear ones first, just for this first time, and then I'll write out the rotational versions. And now the rotational version. For this first one, I didn't have V final. Second one, I didn't have X. Third one, I didn't have time. So now the rotational version. No final rotational speed, no rotational position, and still no time. And that's a good place for me to start. I'm looking first for time. I don't have information about X final or theta final. So if I'm looking for time, I can't use equation 3. Time doesn't show up in there. I don't want to use equation 1 because I have X in that equation and I don't have what the actual value of that is, X or theta. So what I'd like to do is use equation 2. Equation 2 says omega final equals omega initial plus alpha times time. I do know that my initial speed is 0, so I can say T equals omega final over alpha. I get 63 radians per second divided by 7 radians per second squared equals 9 seconds. So I'll plug that into my table because now I have that value. I would also like to know the final position of this wheel. So now that I have the time, maybe I want to use equation 1. Equation 1 says final position equals initial position plus initial speed times time plus half times acceleration times time squared, all rotational quantities. I'm going to move this up just a little bit. And I can just plug in because I have all of these. And it gets a little easier because that one's 0, that one's 0. So I really just have half times 7 radians per second squared times 9 seconds squared. And I can plug those in and I get 283.5 radians. Well, 2 pi radians is 1 circle, 2 pi is close to 6, a little over 6, so this is making a lot of full rotations. If I want to figure out just how many rotations, I might say I'm going to multiply this by 1 rotation over 2 pi radians. And what I find is that I have 45.1 rotations. Okay, these numbers might seem a little bit odd or a little bit strange to encounter, so let me tell you why I chose those. I'm going to go back to the question prompt for a moment, and then I'm going to copy. This is a freeze frame from example 1.2.2 way back when we were doing linear kinematics. Exactly the same problem, except back then I had a motorcycle that was accelerating at 7 meters per second squared, going up to a final speed of 63 meters per second. I asked the same questions and I actually approached it exactly the same way. I will give you a link to the same problem again, to the same example from back when, but I was hoping to make it similar enough to where when you look at the one and look at the other, you can see that we're really not doing anything new per se.